Question 10. Which row shows the bonding in ammonium chloride? Tough question this. You've got to know how ammonium chloride is made. It's made from ammonia, NH3, and hydrogen chloride or hydrochloric acid. So ammonia looks like this. N's in group 5, got 5 electrons in its outer shell. 3 are involved in covalent bonds with 3 H's, and there's a lone pair left over. So these 3 N to H's are covalent bonds. So it's either A, B, or C straight away. Now, what actually happens is this lone pair of electrons is donated to the H, and so that pair of electrons there is from the N. So when the N bonds to the H to form NH4, that lone pair of electrons there, that pair of electrons comes from the N to form that covalent bond here. And when a covalent bond is formed and both electrons come from one of the atoms rather than each of the atoms putting one electron in each, when the pair comes from one atom, that's called a dative covalent bond. So that's a dative covalent bond there. So it's either now B or C. The question is it ionic? Well, when the N gives the pair of electrons away, the N becomes plus, and the Cl breaks off and gets these 2 electrons here, and it has electrons moved onto it, it becomes minus, so you get charges. So it's got all 3. The answer is C. It's got covalent bonds between the N and the H's, it's got a dative covalent bond between this N and this H, and it's got charges because the N has given away electrons when it's formed this dative covalent bond and become plus, and the Cl has become minus when this bond here between the H and the Cl is broken, and the Cl has taken both of the electrons and become minus. How many protons in 6 grams of nitrogen gas? Well, first of all, so the answer is C. First of all, nitrogen is N2, so 2 N's. They share electrons. Actually, N is in group 5, so it needs 3 electrons to fill up its outer shell. So each N puts 3 electrons into the covalent bond. So that's actually a triple bond then, because each N puts 3 electrons in. There are 6 electrons in that triple bond between the 2 N's. Anyway, it's N2, Mr 14 and 14, because the nitrogen has got a mass number of 14, so 2 14s are 28. Moles is mass divided by Mr, so mass is 6, Mr is 28, 0.215. So the number of moles of nitrogen I've got in this 6 gram sample is 0.215. Now 1 mole of gas, 1 mole of anything has 6.022 times 10 to the power 23 particles. So 1 mole of gas would have that number of particles, 0.215. If we multiply that by Avogadro's number, 1.3 times 10 to the power 23 particles. So in this 6 gram sample of nitrogen gas, there are 1.3 times 10 to the power 23 N2s. However, N2 and N has got an atomic number of 7, so an N atom has got 7 protons. It's got a proton number of 7, and there are 2 N's. So in one of the N atoms there's 7 protons, and in the other N atom there's 7 protons. In a particle of N2 there are 14 protons. So I need to multiply this number of particles of N2 by 14 to get the number of protons, and it comes out as 1.8 times 10 to the power 24. Your answer is C. The diagram shows a property across period 3. What is it? Is it atomic radius? No, the atomic radius would come down as I went across the period. Is it electronegativity? No, electronegativity would go up towards the Cl. Is it first ionization energy? You might be fooled by thinking it's first ionization energy here, but Al would come down and phosphorus would go up and sulfur would come down, so phosphorus would be above silicon. So your answer is melting point, and what actually happens here is the Na, Mg and Al are all metals. The reason it goes up slightly is because what happens in metals is they tend to lose electrons, and the electrons move between the ions then, so the atoms become plus charge, 1 plus, 2 plus and 3 plus, as they've got 1 electron in the outer shell, 2 electrons in the outer shell and 3 electrons in the outer shell, Na 1 plus, Mg 2 plus and Al 3 plus. And so the size of the ions increase from 1 plus to 2 plus to 3 plus. The number of delocalized electrons moving between these ions increases, and the bonding in a metal is the attraction between these ions and the delocalized electrons. So as you get in a larger plus charge on each of these ions and more delocalized electrons attracting the ions, then no wonder the melting point goes up as the bonds between the ions increases. Silicon's macromolecular, so it's a large covalent structure, and that's very strong between lots of covalent bonds in a very large molecular structure. P4 and S8 are molecular. S8 has got more atoms, so more electrons, so more van der Waals forces. That's why it goes up slightly, but they've come down, so they're sort of single molecules rather than very large molecular structures. So single molecules, 4 P's, 4 phosphorus atoms in a molecule, 8 S atoms in a molecule, and as I say, the slight increase there to S is because there are more atoms in S8 than there are atoms in P4, and so more electrons, and so more van der Waals force in S8 than P4. Cl2 is just Cl and the Cl bonded together with a covalent bond. And so there's van der Waals forces between these very small molecules, and they are single atoms. They have got full outer shells, so they don't bond even to each other. So they just have van der Waals forces between them. So that's why it comes down slightly. Your answer is D. A 30 centimetre cube sample of nitrogen was reacted with 60 centimetre cube sample of fluorine according to this equation. 0.5 moles of nitrogen react with 1.5 moles of fluorine to make 1 mole of NF3. So let's have a look at this then. The answer is D, but I'll show you why it's D. 0.5 moles of N2 react with 1.5 moles of F2 to make 1 mole of NF3, or I can double that, 1 mole of N2 with 3 moles of F2 to make 2 moles of NF3. And in terms of moles with gases, in terms of the ratio, I can just turn those into volume, because the volume equates to moles. So 1 mole of N2 with 3 moles of F2 would make 2 moles of NF3. I could say 1 centimetre cubed of N2 reacts with 3 centimetres cubed of F2 to make 2 centimetres cubed of NF3. Or I can multiply by 20. So 20 centimetres cubed of N2 reacts with 3 times 20 is 60 centimetres cubed of F2 to make 40 centimetres cubed of NF3. So the 60 centimetre cubed of fluorine is all used up. I've got 20 centimetres cubed of the N2 out of the 30 reacting, and it's going to make 1 mole would react with 2, so it's going to make 40 centimetres cubed of NF3. So what have I got left over in the mixture? I've got 10 centimetres cubed of nitrogen left over. I've used up all of my fluorine, and I've made 40, that should say 40 centimetres cubed of NF3 made. So 10 centimetres cubed of N2 left over, 40 centimetres cubed of NF3 made, 50 centimetres cubed. That's why my answer is D.